maybe I'll just start over. Welcome everyone again. Thank everyone for coming here. I wasn't sure how many people are going to come and attend a talk like this, and it seems like we're filling this whole room, which is great. Thank you everyone for coming. My talk is called The Shape of Shapeless. My goal is to, by the end of this talk, take someone who I hope everyone here is like reasonably familiar with Scala. I'll ask in a second about where everyone feels comfortable at. But take it to the point where you can at least understand why anyone cares about Shapeless and some of the elements of how it works. We're going to go through some concrete examples of how to make it work in a practical and realistic way. But if this is your first time being exposed to this kind of stuff, it might be a lot of material and it might be something that you want to revisit a couple different times. So I immediately want to say there's a Github repo which has all the slides. It has the code, which we'll talk about, and I encourage everyone to download this because we'll do some exercises. You don't need the repo to do the exercises, but if you have the repo, then it will already have the dependencies there for you. There's also a book I made. It's like a 55-page book that were basically my notes as I was constructing this thing. So I would encourage everyone to, after this, if you're curious, if you want to dig more into it, take a look at that book as well. It does everything that we're going to do today with a little bit more detail throughout the whole thing and some extra explorations of different ideas next to it. So with that all said, I really hope that by the end of this talk, everyone in here has some picture of the shape of Shapeless. So my name is Joseph Abrahamson. I've been programming professionally in Scala for like a little over a year now. Before that, I did a lot of Haskell stuff. I've done a lot of type crazy stuff before, and sort of when I dug into Scala, I was like, all right, let's see what we can do here. And I spent a lot of time exploring some of these type level tricks and powers and capabilities that Scala has. Scala has a lot of power, and there's a lot of really interesting things you can do, and a lot of that culminates in Shapeless. So really quickly, in case anyone doesn't know why they're here, this is Shapeless, as most people are aware of it. It's this library put together by Miles Sabin, and it shows up in a lot of places kind of unexpectedly. A lot of libraries will use it, but you might, by and large, not ever actually have to see what's going on in Shapeless. It'll be a dependency and it will give you some powers, but you don't ever have to touch it per se. Or rather, when you do touch it, it looks like that, which in case anyone can't see that because it's a little bit of a small image, that is a type error which tells you next to nothing about why the error is happening. And that is one of the big issues with Shapeless, and I think probably one of the first interfaces that people have with it, very unfortunately. It's magically helping you out in some way that you don't really see or care about, and then it's really not magically ruining your life as it breaks. So hopefully the shape of Shapeless, again, is me helping to kind of unwind a little bit of at least why those are inscrutable errors, and some of the techniques you could do to start to see why they might be happening and start to debug them, all the way out to you can write and use Shapeless as a master Shapeless user, whatever that would be called. All right. So what is Shapeless for real? Here's one picture of it. Shapeless is a Scala library for type level and compile time generic programming. There's other things that you can do with Shapeless. Shapeless is sort of like a launching off point to much, much more interesting things, but kind of the real reason why most people use it is compile time generic programming. So I'm going to define type level programming and compile time generic programming now. Type level programming. This is something that maybe gets talked about in various corners of advanced versions of Haskell or Scala or Rust. I don't know about Rust, Swift. Other languages that have complicated type systems, C++, you do type level programming. And what happens there is you create a program and it runs at compile time, unlike at runtime. And it actually works off of the types, and maybe it takes some input types and produces some output types. Or very, very interestingly, and what we'll be doing today is it takes some input types and actually computes both output types and an output program, which then gets compiled and run later at runtime. So it's actually very powerful, and you can do some very interesting things that are sort of related to what you might use macros for in Scala or in other languages. Compile time generic programming. So let me talk about generic programming first. Generic programming is the idea that it's why a Python programmer moving to Scala doesn't understand why anyone would want to use Scala. Because they're used to the idea of thinking of a piece of data as being a collection of different pieces that you can kind of pull apart and rearrange and stick together again however you want. They're used to structurally typed ways of working with data. And the first thing you run into in Scala is you define a type, and then it becomes a name. It's no longer like a point in two-dimensional space is no longer just a double and a double. It's a kind of concept all on its own, which we all know is just a double and a double, but we have to do a lot of hand-waving and work and boilerplate in order to re-access that kind of simplistic structural form of it. So generic programming is, in a nominal language, a language like Scala, how can we get back to structurally feeling how we program things? How can we program things over the structure of types? And compile time says we're going to do it all at compile time. You can do this with reflection, for instance, in Scala. If you've ever used product iterator, that's a structural kind of generic programming kind of approach to doing some work. But there's some drawbacks with doing reflection-based things, which I'm not going to get into maybe till the end. And compile time is another approach that maybe is a little bit safer and maybe allows you to do some of that work before the program runs. And at the very least, it's another approach to doing those things, which Shapeless makes available. So that is my definition of Shapeless. And again, I'll go back to the kind of common definition of Shapeless that many people run into, which I really want to be empathetic to, because this is one of the worst parts about type-level programming, is that it's going to create a bunch of inscrutable function signatures and a bunch of error messages. And using Shapeless effectively is avoiding those, making it so that you make something that is useful to users, but never kind of causes them a lot of pain. And so that's another thing that we'll talk about as we go through an example of using Shapeless, is how to do that kind of balance. And so with that, let's dig into the shape of Shapeless. First thing I want to do is, everyone here, this is an advanced Scala course, so can we get a raise of hands of who has used Shapeless before or done any of the stuff that I might be talking about today? So you guys are the experts, and when I don't know an answer to someone else's question, I'm going to call on you guys. Who here has used Shapeless but has no idea how it works? Like, you used it in a library or just ran into it somewhere. Maybe you've used Circe, the encoding decoding library, which uses that, or some of the other ones that do that. So a few more hands. Who here would consider themselves to be like a really competent, like you feel comfortable with Scala programming, you know all the basic things for Scala, you can do all the stuff you need to do, but you've never touched any of this and you've never cared? All right, cool. So kind of thirds. Awesome. I'm going to assume at least that much, and that I'm going to introduce a bunch of Scala concepts pretty freely. I'm not actually assuming that everyone knows what those are. I am assuming that if you don't know what I'm writing on the board or what's in the slides, that someone will ask a question. I really like more interactivity, so if you have a question, just ask it. We'll not get too derailed. We'll try and figure out how to get everyone moving along together, and yeah, just please ask your questions. So with that, I'm going to try and say, for the purposes of this presentation, what Shapeless is in 3 pieces. It's the concept of using really rich type-level information. And by rich type-level information, I mean that the types themselves are big. They're big, complicated things, which can be annoying, but it also means that there's a lot of information that can be picked apart in the same way that, like, you might pick apart a tree of case classes. There's all that information in there that you use as you write functions. We need to get our types to be rich enough so that when we do type-level programming, we have a rich space of things to play with. So Shapeless gives us rich type-level information. We exploit that via this technique of type-level programming. And I'm going to say probably maybe over 51% of this talk is going to be us exploring some type-level programming. Type-level programming, as I said earlier, is computing on types that return types or return other programs. And Shapeless is embodying kind of one well-tested approach for doing this in Scala. There are some things that are more standard. There are some things that are less standard. I'm going to try and give like the happy path for how to do type-level programming in the way that Shapeless exemplifies. And Shapeless provides a lot of tools to help you do that more easily and more quickly once you kind of get the basics down, in the same way that when you first learned recursion, that was something you had to learn, but then you learned mapping functions and fold left and things like that, and these higher order patterns. Shapeless provides a lot of those higher order patterns that make type-level programming in a certain style easier to do. So the second thing is type-level programming. And the third thing is compile time generic programming, which is what we just defined a minute ago. So there's more that Shapeless can do, but this is sort of the core pieces of it in the way that I want to present today. And so with that, here's what we're going to talk about today. Pretty much those things. We're going to talk a little bit more about why all this stuff matters to begin with. And then we're going to spend, I wouldn't say thirds on 2, 3, and 4. I think 2 is going to be fairly fast. 3 is going to be fairly long. And then 4 is going to be a little bit shorter. And I'm going to put exercises that we're going to do after section 3 and section 4. It really depends on how quickly we get through this material. I've done this talk and it lasted like an hour, and I did it and it extended into 2.5 hours. So like, it very much depends on people asking me questions. If you don't ask me any questions, we'll be out of here in 25 minutes and you have to do all the exercises there on your own. Not true, but we'll try and take time with those exercises to give a chance for people to discuss, work together, ask me questions, run into walls, and then maybe do them together if we have enough time to get into the exercises that long. So with that structure, that's what we're doing here today. Does anyone have any questions yet?
Do you have a pointer to your repository, you said?
I will write that on the board. The repository is on GitHub for a little while longer. Not yet. Tell, which I didn't mention it. If you're looking for me. Thank you. I'll write it bigger too. All right. GitHub joke. Tell, if you're looking for me anywhere online, I tend to go by that. It's my middle name. And it's shape of Shapeless. No spaces, no dashes. Caps don't matter. Cool, thank you. In this repo, again, it's just a Scala repo. You should open up using whatever Scala environment you're most comfortable with. I'll use IntelliJ later. It also, like I said, has access to the slides. There's a PDF in there. There should be a PDF in there. There's also the raw markdown, and it has access to that book I was saying. There should be a PDF that's like a 55-page book that you could follow along with this presentation. It's literally the same outline. It just goes into more detail on everything.
Question. Are there any other libraries beyond Shapeless that do the same thing which allows us to type level programming in Scala?
I am not familiar with them personally in that Shapeless, I think, dominates a lot. Although I literally was listening over a conversation yesterday at lunch where someone's writing a competitor like right now. So more ideas are coming. Shapeless is certainly not the only way to do this stuff by any means. So there's definitely room for other people to try other ideas. I think it dominates right now in the market though. Cool. Let's dig in. So I already started talking about this. I want to motivate generic programming. So maybe I'll start with that. Who here would be able to define to a colleague of theirs what generic programming is? Awesome. Okay. Either that's because that word is very vague, or it's something I should really talk about right now. This is the example I kind of highlighted earlier really quickly. Let me give you a definition. This is, oh my god, I just thought about how, can people see that?
Yep.
Okay, cool. I can change the contrast if it's not visible, but I just realized that's light green and light blue and white. This is a case class you might write in Scala. It represents a point in 2D space. It might be part of like a graphics library or a linear algebra library, who knows? Like it's a concept that's really important. And in some sense, like what it represents is in space, some point right there, right? When we work with point 2Ds, we really want to be working on things like translate by some vector to a new point, a nice spatial concept. This is domain modeling, right? You build case classes, you build types, you give them names to represent the information you care about and represent the operations that work on things in your domain. But on the other hand, it's obviously two doubles. Now that's a representation thing. You don't have to represent it as two doubles. You could represent it in other complicated, weird ways if you wanted, but that one's two doubles. And I would like to exploit that information. There's the translate function, applying some vector to shift it. And in particular, I would like to exploit that information when I'm writing things that are not really part of the domain, but are more like very practical kinds of things, like ordering. Like, I want to be able to sort a list of points. There's not really an ordering on points in space that's too good. You can maybe do like distance from the center, and then you have a bunch of points that are all equal to each other at the same distance. I don't know, whatever. There are a lot of different orderings you can do on points. Maybe I don't really care about that ordering. I just want an ordering so that I can sort the points because that's really convenient for the way that I'm data munging right now.
Excuse me, can you do a right shift?
There's one more chair down here, right in the center.
We got an extra sequence. Everybody just move down one.
That might be a lot more difficult.
Yeah.
Inserting himself.
Okay. Well. All right. All right. So I guess what I'm trying to argue here on this slide is the idea that when you make case classes and you have this very nominal world, domain-driven world, a lot of the functionality you want to write is specific to that domain. But there are many times pieces of that functionality that you don't want to write, and it's not very specific to that domain, and it's kind of boring. In this case, compare is my target. I would have used equality, except Scala gives you case class equality, so it's kind of both helping my argument for this and hurting it in that I can't demonstrate equality very easily. You'd be like, why the heck would you use Shapeless? Scala's just giving that to you. But also, Scala gives you equality on case classes because if you didn't get it for free by Scala, you'd have to use some techniques like this to do it manually because I don't want to write my own equality for points most of the time. I want to do the obvious one. I want to do the one that just treats it like two doubles. And so that's what I want to argue here. For pretty generic functionality like compare, it's really important sometimes to not have to care about that, to just have a right implementation, to have it just use the structural information there. So again, structurally, the way you would treat that is as two doubles. And we can have very nice ways of defining ordering over things like two doubles that work extremely generically. This is just a common pattern using Scala's type factored out to the T. If you can compare two things, you can compare a tuple of two things by just comparing them lexicographically, which, by the way, just means the first one and then the second one. So why can't we use this instance, lexicographic ord, for tuple, or for point 2ds? Like, that's a really great question. It doesn't work, but it really feels like it ought to because we all kind of know, based on that case class definition, that a point 2d is just two doubles. So it should work. One trick that you might think about doing is trying to say point 2d should subclass double-double or something like that. That would be one technique to sort of begin to get this kind of functionality for free. I'll say one thing, I don't know if I'm going to really demonstrate it in this talk, that doesn't always scale very well as you start applying that to different types. Long conversation, not for today. But also I would say it is actually just not really domain or nominally valid for point 2d to inherit from something like tuple 2 of double-double. Because it's not really a tuple 2 of double-double, that's just a coincidence that we're going to exploit. But it's just a coincidence about the way that we're representing a point in 2D space. Again, I could represent it as like a rotation and a length, or I don't know, some other kinds of things. So does that kind of make sense? This idea of the nominal world and the structural world sitting right next to one another, but you can't really commute between the two very easily in Scala. And the idea with generic programming is that it gives you an avenue to get that commutation between the two, and we'll actually answer this question in the positive by the end of the day today. We'll use that lexicographic ordering more or less to automatically get one for things like point 2d.
So,
Hi.
I'll ask a question, something related to how you just reasoned about saying that it's not really tuple 2, right?
Mm-hmm.
It's similar to how we reason about when you're in the object-oriented world like this. Like it's not necessarily a subtype of something.
Mm-hmm.
Is this how we even go about solving in the functional world? Like, we also bring about object-oriented concepts trying to define whether something is type or subtype.
I see.
Because the way you try to reason out is just like how we do in the OOPS world, right? This is how we also do in the functional world to decide whether something is a type or not a subtype. I mean, we're talking mixing two types, right?
Yeah.
In Haskell, which is more purely functional, how do you reason about it when you come across situations like this? Even though it's not Haskell,
I think I can talk to that. That's a really big question. I think I can talk to some pieces of what you're saying. So the question was, I think, what I just described there was sort of comparing subclassing and comparing this generic versus structural versus nominal. Like, there are different ways of abstracting a piece of data. And obviously, subclassing is something that's very popular in object-oriented methodologies. Is this something more commonly done in kind of a functional aspect? And I would say that yes, that could be kind of a true thing. I don't want to speak too broadly about what functional programming is because that's a long conversation as well, but this idea of using subclasses to represent how things are something or another is a vocabulary that's sometimes really valuable, and in this case I pointed this one out to kind of say I don't think that's a valuable way of doing it. It's not a has relationship, it's not an is relationship. You just kind of notice it. A point 2D is the same shape as two tuples. I noticed that similarity exists. And they have no meaning linkage. They're not is or has or something like that. So I almost want to say, if I only could use subclasses, I would run out of things to say right now, perhaps.
So, two things. One, you might consider a type alias. Right? Point 2D is the type double-double.
Yes.
The other is that what you're really noticing is an isomorphism,
yes,
which suggests using implicits to go back and forth between them.
And I think that's exactly the first thing we wouldn't want to do, because we want point 2 to be its own thing.
Right.
But then we happen to notice this isomorphism exactly. We happen to notice this correspondence, and we want to be able to exploit that too. But we don't want to exploit it using subtyping or subclassing, because then Scala is going to automatically convert our point 2D into doubles whenever it wants to or whenever it needs to, and that's not right. They're not two doubles. It's its own thing. So by noticing the isomorphism and building this type class representation of it, then we start to talk about this as its own thing that we want to manipulate. Sometimes we want to use it, sometimes we don't. In the case of, I want free comparisons on point 2Ds, and I don't really care what it is because I'm just going to put them into a list. Hey, it's great. I have this isomorphism. I'm going to exploit it right now to get a bunch of free code. But I don't want to have it happening to me all the time. So I think that what you're saying relates to that very nicely and is a good way of looking at it. And did that kind of get to what you're asking as well? All right, great. So we talked through a lot of these different things. Here is a way of exploiting that information. If I write a two-tuple function, I don't even need to use the whole isomorphism here. I just need to convert point 2Ds into tuples in order to use lexicographic ordering, because I never need to go back. But I could do it like this. If I really wanted to, I could do that every time I see it. I could do a little 2, whatever the other type is, and then use it to write my stuff, and I don't want to write any of that. I'm tired of all that. So to be clear, I'll kind of record scratch and step out of the scene for a moment and say, a lot of what we're going to be doing here is boilerplate reduction. So maybe I should spend a half second motivating that. There's reason to believe you shouldn't be too concerned with boilerplate reduction, like it makes things complicated. This will make things complicated, totally. It makes things less obvious, like maybe you should just be copying and pasting code. There's a whole world of people that think about that. I think that's a reasonable thing to think about. For the purpose of this talk, we hate boilerplate. It's terrible. It causes errors. I'm going to get rid of all of it. So yeah, that works. That's totally fine. There's a bunch of ways you could mess that code up. Do you trust everyone on your team to never mess that code up? Of course you do, but let's not. We want to do it all automatically. And that's what we'll do. That's what we'll do today. And then I want to bring this up because I feel like this is a place that a lot of people encounter this. Who here has used Circe or some other automatic JSON encoder decoder library? Yes, I'm going to get all of you. A lot of these libraries have leveraged Shapeless or tricks like this because they didn't want to, maybe they started with macros or they use macros a little bit, but there's this general idea that compile time generic programming does the really cool thing of taking all the case classes you've got and finding a natural way to represent them as JSON and to go back and forth between the two. And it's a real sweet spot for using this kind of technique. And it also is one of those places where people run into terrible inscrutable error messages because if you put things in slightly the wrong order, suddenly Scala can't find some implicit, and it just likes to tell you, oh no, I can't find the implicit, instead of helping you out to know why it can't. Anyway, we'll get into all of that stuff, but I just wanted to bring this up because it's really lovely. It's a good application of this technique. You've probably used it, and you may have run into these pain points, and I'm going to hopefully start to demystify how Circe works somewhat. Although, as a small caveat, it uses macros in there too that we will not be talking about. Yeah, that's what it looks like for anyone who hasn't used Circe. And actually, I want to emphasize this. The thing that's really cool about this is the one-liner here, semi-auto derive encoder. We will be writing one-liners like that. We'll be defining one-liners like that and using them in this workshop today. All right, cool. Does everyone love generic programming and really want to do it now? Are there any questions about why we do this? Awesome. Then let's dig into how Shapeless does it. like I said, Shapeless, the first thing we want to do is we want to represent rich type information. We do that with this thing called HList, heterogeneous list. Not homogeneous, not the same, different kinds of things in your list. Right. I want to be extremely clear. Here's another kind of heterogeneous list that people will often use. This is not the one that I'm interested in. It works, you can do things with that, totally fine. Not saying anything against doing that, although I am going to say something against doing that in a different world. But right now, that's totally fine, whatever. It's just not heterogeneous list. And the reason why is because list any is not a rich type. It's a really boring type. It has two pieces of information, list and any. And any is a really not informative piece of information to have. So I don't want that. I want something way more complicated, like tuples. Tuples are H-lists, actually. This is pretty much the whole concept. A tuple gives you all the information you could possibly want about what's inside of it. It tells you all of the things inside of it, the order that they're in. All of those things are fixed, and it has all of the information up in the type. If I were to treat the tuple type as a value, I could start pulling information out of it and do anything I needed to. And that's exactly what we'll be doing for the rest of this. So tuples is H-list. We're done. Next section. But not quite. Anyone have guesses for what's wrong with tuples?
You can't map over it?
Well, you could, if you wanted to find 22 different ways of doing it. They're...
It can be enormous. What types of tuples?
Sorry?
It can be in any number of types, right? In tuples.
Well, we kind of want that. All the different types in the tuples is the information we'll be exploiting. It's just, oh, you have a guess too? Yeah. Done. They're annoying. That's the answer. This is something we kind of expect, like tuple 3 should be pretty closely related to tuple 4 and tuple 2. They are not. They're just all subclasses of the same thing, and there's not any obvious way to map between them. Unit really ought to be a tuple. It's the tuple of nothing. It's got essentially zero relationship to tuples. To write functionality for all tuples, we need to write 22 versions of anything we want to do, which is not just 22 versions. It will be exponentially growing as you start to combine. It doesn't work. And, oh yeah, we only have up to 22. I don't really recommend case classes with more than 22 things, but they happen, and tuples can't help you suddenly. So I'm going to read, here's the previous example, int boolean string list of int. This is the exact same example again. Int boolean string list of int. I just wrote it differently, still using tuples. It still has all the same information up there too, right? We've got, how many? 5 types in a certain order. They're the same types. It's just instead of using up to tuple 6 or 5 or whatever, I just used unit and tuple 2 only. And what's nice about this is, well, let's do that. What's nice about this is it's a regular structure. I'm only using 2 pieces. Instead of having to define 22 versions of something, I just define something for unit, and I just define something for tuple 2. And then this thing can use recursion, which, by the way, we'll be doing type level recursion later. Really fun stuff. You can use recursion to drill through that type and pick it apart piece by piece by piece. So this is suddenly very easy to work with. The tuple 2 analog here is extremely closely related to the tuple 3 analog because you just slap an extra layer of tuples on it. So this is really what an H-list is. And I'm going to change the syntax on you in case anyone has not seen infix type syntax. You can do it. We'll get more into this in a second. So this is the same type as the previous one. I just changed the names of the types a little bit. You don't have to write it on a bunch of different lines now. And here is H-list. This is 95% of the exact definition out of Shapeless. It's not actually very complicated. It fits into a couple lines. It's just tuple 0 and tuple 2. So let's go into it. 1, there is a supertype H-list. It'll come in really handy later. Then there are 2 elements of H-list. One is H-nil, and the other is this ... thing, which I'm going to happily call H-cons from now on. It's an infix type, just to be clear. If you define a symbolic type like that of 2 arguments, it can be used in infix position in types, and Scala just figures out what you mean. And it's essentially just tuple 2. The only thing interesting about it is that we don't call it _0, _1. We give them suggestive names. And the right half of tuple 2 has to be another H-list. Tuple 2 is a little bit more powerful than H-list because you could stick anything on the right side, but we don't want that. We always want our lists to be kind of linked lists, not trees or anything like that. So the only other trick here is the object hnil is the same as or there is an object called hnil, which is the only instance of the type called hnil. So hnil exists at the object level and the type level. : hcons exists at the type level and the value level. And it also, I didn't write it here, but I don't worry about it. Hcons and hnil both exist at the type level and the value level. And it'll be a little bit tricky to figure out at first, but then we'll practice and we'll get better at just figuring out when they are. Yes?
So is it analogous to the Scala or list cons operator, or is there some subtle difference?
The only subtle difference is just because it's all operating at this, because it's operating with like the tuple idea as opposed to a list idea, you can have the heterogeneousness of it.
Okay.
And it's going to create a really complicated type as you cons things together.
Right.
Like,
Well, yeah, I follow.
yeah, just that's a really good question, so I'll just write it out. H_nil is a value, and it has type H_nil. 2 Hcons H_nil is a value, and it has type int Hcons H_nil. So this, if that makes sense to everybody, then we are golden. This guy exists at the type level and the value level, type level, value level. They relate to one another in exactly the obvious way. Hopefully that doesn't get too confusing, but it is worth keeping in mind that they're different.
Can you go back to the nested tuple problem?
Sure. This one?
Yes, I'm wondering if this is protected to the same 22 argument constraint.
No.
No.
That one can grow until you run out of memory, I guess, at compile time.
So every time I create a new one, I'm creating a new tuple because it's supposed to be mutable.
It's not going to be mutable. It's just that if I have a tuple of some size, like a tuple of this style of containing 4 elements, I can make it contain 5 by just wrapping a new tuple around that. So the left side of each tuple is a value, and the right side is another like big collection of tuples.
It's analogous to a linked list.
It's exactly that. Yep. He said it is analogous to a linked list. Which, yes, all of these are linked lists happening at value level and type level, and just a more complicated version that allows for the heterogeneousness and, the, again, rich type level information. Cool. So heterogeneous lists with any ain't no kind of heterogeneous list. That's not what we're talking about here. It just isn't interesting. You can't do anything fun with it. Tuples are the generators of rich heterogeneous types. Are there other ways to do this? I want to just go ahead and, again, record scratch, step out of the situation and say, there's a whole nother level of rich type level information that I'm not going to talk about today called coproducts. I'm just going to not do it because we don't need it to do some very interesting things, and it all kind of works analogously to what we just talked about. So, back in. We're going to create rich heterogeneous types with H-lists, and they use this recursive structure in order to create that richness and have it be regular and easy to manipulate. An H-list is just unit in tuple 2 with new names and slightly more constraints on it. All good? In that case, I'm going to jump into actual type level programming. So this is all the easy stuff. Now it's going to get weirder. Any questions before we dig in? Awesome. All right. H-lists are great and all, but you can't do much with them. In the sense of, great, I created all this really rich type information, and if I try to write any functions on it using any of the techniques that you're used to, you'll find that you pretty much can only write from a specific H-list to another specific H-list, or a specific H-list to some other output. Like, you need to know so much about it. And the whole point of H-list was to have recursive and kind of generic structure, and we can't exploit any of that. So I want to be able to write something that's sensitive to that rich type level information. That's what type level programming is doing. How do we exploit that? So some questions, like, does concat like that do anything particularly meaningful? You can write it. It works. I didn't write it, but you could write a function like that. I'm going to argue that that's not very meaningful. We're using H-lists, but because we jumped up to the supertype, we forgot all the interesting information. So that's pointless. Is it any better if we make it generic like that? It could be. And that this is going to work for any 2 specific H-lists now. without forgetting what the types of your inputs are, but it actually forgets what the type of the output is. Like it just gives you an H list out, which is again useless because we've thrown away, as soon as you call concat, you threw away all the interesting type information you have. So one way of thinking about type-level programming is programming is sensitive to rich information, and also it preserves rich information. If it were to just throw away the rich information, then we wouldn't be able to get very far with it.
I've got to object to that. It seems like if you did that concat, you could still preserve the type level information in the return H list. It would just be the concatenation of all the types.
That's what we'd like to do. The way that I've defined the signature right here, because it just says the output is some H list,
But that's what we're going to be moving.
we'll be doing that. Yeah, we won't actually do that today because I didn't do concat as an example,
Yeah.
but you could.
I think that's cool.
You should be, after the end of this class, able to write that on your own. Was there another question? I thought I saw a hand. Okay, cool. So we need type-level programming techniques to do this. So here's an example. The first example we'll do. It's a function called speak. It takes in an H list, and it does something kind of funky. It's actually going to be very sensitive to the actual types of the elements inside of it. In particular, all it's doing is it's turning all the integers into strings by stringifying them. It's not doing anything interesting functionality because we don't care about interesting functionality yet. We just want to do the technique. So what I want to ask is, does everyone see both what speak is doing, like what the specification of speak is, and then also, does anyone have any questions about why you might need some kind of new technique in order to write a function like that? You couldn't just use basic value level programming.
Those other integers are wrapped in the seek, and you can't speak the seek yet.
We don't even want to speak the seek, right? It stays as a seek. But yeah, like being sensitive to the fact that you've got a seek here and it's got maybe integers inside of it, but we don't want to go there. Like that whole idea, that logic can't be encoded at the value level because it's actually the input to your logic was the type of this. And so another side note, you could totally do it by just doing like is instance of and things like that. So I should have mentioned that earlier. I'm going to outlaw all kinds of reflection things. You can do lots of things with reflection to get this stuff done. Again, I'll try and argue at the end after we've had some familiarity with it of why this stuff might be preferable to that. But sorry, reflection is totally outlawed for the next like 45 minutes at least. So we can't use reflection to do that, otherwise you could. Also,
Shapeless use it, reflection internally.
Shapeless is going to use macros to generate a piece of technology we'll use later that ultimately, it's not going to use any runtime reflection at all. 99.9% of it doesn't use any runtime reflection at all. If you go look at it, you'll find some. But the stuff we use today will not use any runtime reflection, and it uses some macros to generate some information, which is another kind of reflection, but not the same.
Sure.
Right, so yes, this has to be sensitive to types, and we're not going to use isInstanceOf to do it that way. And for what it's worth, I didn't really state it here explicitly, but the output type of this needs to be interesting too. The output type needs to be string, hcon string, hcon string, hcon string, hcon string, hcon seek event, hcons hnil. I should have made a smaller example. But if the type is not also sensitive to our transform, then we aren't really going to be doing interesting type-level programming for very long. And again, that's what you would get if you used isInstanceOf, because you wouldn't be able to tell it, well, I know the type has these nice properties too when it comes out. That's kind of the downside of doing things at runtime. You can't change the types. All right. So if it's clear why that's interesting and why it's not obvious how to do that, I'm going to dig into what we need to do in order to do it. And it's going to be totally prescriptive in the sense of I'm just going to tell you the way that you do it. It's the garden path of type-level programming. There's a million different ways to jump off of this path. I'm going to just give you the garden path. And I'm going to expect you guys to ask questions about why I chose to do these things. Otherwise, we're just going to zoom through it, and I'm going to give you like my condensed, Shapeless-inspired best practices for writing type-level functions. Sound good? All right. All type-level programming begins with a trait. The reason for this is because we need to abstract over types, which means we need to be able to talk about a trait that applies at different kinds of types. So in particular, it's not just any trait, it's a trait with a type parameter. So this is the one we'll actually be using. And I want to just make sure is this, like at least functionally, in terms of understanding Scala, does everyone have familiarity with what's going on here, or any of the things that I'm doing here unfamiliar to everyone, in which case I'll explain them.
Just also, contravariance gets tricky. Can you explain what has to be contravariant here?
I think it doesn't have to. When I'm building, I'm going to build up through a couple wrong versions of it, and the wrong versions we're not compiling without that. But I think the right version actually doesn't need it. That's just an artifact of how I built the slides. I didn't check that, but I think. I think. Any other questions about what exactly is going on here? So I'll start explaining kind of the way that I read this from a type-level programming perspective. Any type-level function, at least if you're writing it by hand, in the same way that you write like manual recursion when you first learn how to write functional programming, and then later you use map, any like manual recursion style type-level function that you want to write is probably going to begin with a trait. You're probably going to name the trait the capitalized version of whatever the function that you're going to write is, and the trait is probably going to take a type parameter. Type parameters are the things that will allow us to be sensitive to input types. That's why I labeled it in. You could have multiple type parameters, but anything as a type parameter you want to think of as an input type. In this case, I've also got an output type, a type member, which there's always this complicated thing of like, when do I use type parameters versus type members? And it's always there's ways of kind of doing everything with a type parameter that you could with a member and vice versa. In this case, this is the way you do it. If it's an input type, it's a type parameter. If it's an output type, it's a type member. It just doesn't really work any other way. It could, but it shouldn't. And then inside of this, so what I want you to think of is if you ignore that apply function, this is kind of like a type level function all by itself. It's got an input type and an output type. And if we instantiate a bunch of speak instances, then we could use that to build some kind of type computation. The apply method is when we get to the code generation part. When I do that type computation, I put an input type in and get an output type out. I'm also going to get an apply function out, which I wrote incorrectly here. I apologize. The in should be of type in, not generic hlist. I apologize for that. And the out is type out, obviously. So this is not just saying that this function transforms types from in to out, but it also has a value level, transforms values of type in to values of type out. So you can kind of see how this is exactly what we need to do the thing that we couldn't do a second ago. Speak takes in a complicated hlist type. It returns a value of another different but related complicated hlist type. So in is going to be the input type, out is going to be the output type, and then apply will be the thing that actually performs the speaking function by transforming the input type of hlist to the output type of hlist. So this has all the things we need, and that's kind of what you get with these. I'll say for some type level programs you don't need an output type. One of the examples we'll do later, or the exercises I'll hand you guys, does not need one. It's a little simpler then. You don't always need to have the apply function if you only need to operate at the type level, but speak is one that both manipulates types and creates values, has an input and output, so it has all the jazz. That's the generic template for it, more or less. Sound good? All right. Here's the first way I want to think about writing type level programs. We've defined the trait speak. Now I'm going to build a little DSL for building values of type speak such that I can only build values that actually implement speak properly. Like I can't just pick any input and output type. They have to be the ones that actually do the specification of speak. So I'm going to build this DSL for constructing speak values. I'm going to use that to do type level programming. So we'll start with the simplest one. I know speak of h-nil because speaking of h-nil is just h-nil. I don't do anything interesting to that, right? So I'm just going to define a speak instance. Literally just using new speak h-nil. I know the output type is the obvious output type. I know what apply does. It just passes the input right through. h-nil is the degenerate case. So here, I've begun to build this DSL. I know how to do speaking over the simplest kind of h-list, h-nil. And then we make it more complicated. This is the recursive step. It says, I know how to speak when I have an integer on the head of an h-list. But I can only do that if I also know how to speak to the tail, right? So I've got a recursive step. I'm able to grow the complexity of my speak values by one element. And the return shows exactly that. The return type of this function is a speak that works on h-list of type int, hcons, sum tail, whatever that might be. So you can already see, just from that type signature, if I start gluing speak h-nil, I should have left that up, sorry. Does everyone have the repo address who needed it or wanted it? Okay, great. Speak h-nil has type speak of h-nil. Speak int applied speak h-nil has type speak of int hcons hnil. So you can see that this is growing the space of proper input types I can apply to speak. The functionality I have to give an apply, in this case, because I know that the head is an int, and I want to be sensitive to ints, I want to turn those into strings, the apply is just going to take the toString of the int. And I'm deconstructing that input hlist using head and tail, as you can see as well, which is, again, just those are methods on the hcons type. I'm going to write another one of those, which is basically the exact same thing, but it works for when the head is not an int, right? Because if it's not an int, I want to just preserve that type. I don't do any transformations to it, and the output hlist has the same type as the input hlist. And so that's what this one reads. You can see, just like the previous one, you need to have a tail speak value, which handles the rest of the hlist. It returns a speak of something hcons onto the tail, so we've expanded the size of that hlist by one step, and that expanded thing can be any type head that I want. So it could be string or seek of integers or whatever. And in this case, you can see that the apply function is just passing the input head along unchanged. So I just threw a lot of stuff out there really quickly. I didn't even talk about all of it yet. Yes. I really want questions at this point, because I'm expecting that this is a lot of material, at least if you've never seen it before, or if everyone actually does understand that this is going to be a really short presentation. So please ask questions. Yes?
What stop you from passing it into the non-int speak?
Sorry?
You can pass it into the non-int speak, right? That's just by convention you're not supposed to do that? Is it
Yes.
Okay.
You broke one of my exercises. But exactly, yeah. My DSL is actually covering more functionality than speak actually is supposed to have. And that's a problem. We'll fix that problem later. Any other? Yes? Oh, yeah. So the question was, he noted that I can use speak non-int even when head is int, which breaks my functionality, because now it's going to not transform one of my ints to a strings. So I just have to promise myself that I'll never do that. And then later we'll show how we can not make it so you never ever do it, but make it so that nobody in their right mind would do it, which is an improvement, I guess. But yeah, in general, my DSL is covering more space than what speak actually is, and I have to ensure other properties to make sure they glue together to actually do speak properly. Yes?
Can you show the first one with nil? Because I still don't see how, no, the one with nil.
That one.
Yeah, I see. Okay, thank you. Still couldn't figure out how to call any of these.
The way that you call them, that's on another slide later, but the way you're going to call them is you're just going to construct a speak value for whatever the appropriate h list that you have is, and then you call .apply on it and you pass in the h list. So I want to emphasize right now, I was going to do it in a second, but I'll say it right now. This is not really the way we type level program. This is like a backbone to it, because it's way too much of a pain in the ass to do anything that I'm describing right now. And the one last thing that I didn't talk about and no one asked any questions about is this out type. You can sort of start to see how the input is the input and the output is the output, because I can define type members as, I don't have a mouse, I don't have a laser, and that's the wrong slide. I can define type variables in that def, like head, and just declare that that's the kind of input that I'm looking for. And then I can actually use those to construct whatever output type I expect to be there. So for this one, head gets passed through directly. For this one, I say that I'm expecting an int as the input, but I'm going to get a string output. So that's how you get this input-output relationship with the types.
Can I request something? Can
Yeah.
you please highlight what on the slide when you're possible? I don't know.
Can you see my mouse? Nope. Sorry.
If you highlight something, does it show up there?
I can't highlight, it's a slide. The thing I was talking about was the type out equals thing, versus where I'm defining the inputs is that at the very end of the first line where I say colon speak int colon tail, I'm saying that for an input of int and something, the output is going to be string and that same something, or actually the transformed something. So that, it's something that we'll practice later, but I'm trying to emphasize that the reason why type members are outputs and type parameters are inputs is because when you define definitions like this, you kind of have access to the inputs as inputs, and then you can choose what the outputs will be. So I think that's stuff that we'll get some exercise and it'll make more sense then. Right, so this is the thing I was saying. Here's an example list: string, string, int, seek of ints, and then a value of it. I can build a speak value that matches that. And then I can, oh yeah, right. I mean, I could apply, did I actually show it? No. If I do xlist.apply and pass in, or xlist speak.apply and pass in xlist, then we'll get the right output type. Obviously, that's terrible. Like, yay, I just saved you guys a bunch of boilerplate by making you write a bunch of other more complicated boilerplate elsewhere. So that's not the right thing. It's not scalable, and we're going to need to get Scala to write those instances of speak for us, which hopefully everyone's already kind of guessed the punchline here if we're going to use implicits. Implicits are a really great way of using type information to get Scala to write stuff for you. I want an implicit ordering of doubles. I just ask for it to exist, and Scala's like, oh, I've got one of those here. And as it turns out, implicits are really powerful, and we're going to use them to have it write this value for us, knowing only that we're interested in having a speak value for some example hlist. So that's the next step. I'm going to talk a little bit about this. I'm assuming everyone has some familiarity with what implicit resolution rules are, by which I mean some, because there's like a million of them and nobody knows all of them. We're going to put everything in the companion object, make it simple. The important thing to think about, though, is the important thing to think about is we're going to define implicits of kind of two kinds. One are what I call terminal kinds, which is exactly the terminal that we just did there. Speak of h nil, it terminates the recursion happening here. And the other is rule kinds. If I can implicitly find this, then I can implicitly find that. And it turns out implicit defs, which have only implicit arguments, do exactly that. The implicit search will say, oh, that def will give me what I'm looking for, but I can't get it unless I can find arguments of these types, and it will go and find those arguments, and if it fails somewhere, then it will backtrack, and it does this whole prologue thing. But you can just think of it as terminals and rules, and we're going to build a set of terminals and transition rules that will build these speak objects for us. And in fact, we just did. Like, I'm not fooling anyone here, I hope, at this point. I think, yeah, I was just explaining that. Type directed search, that's what we're going to do. I'm just going to take the things that we just wrote and stick implicit in front of them. I'm going to take the defs, and I'm going to change the arguments to implicit args. And it works. That's all it is. This kind of thing is exactly the structure I'm looking for. The h nil is a terminal case, so if I implicitly ask for the ability to find speak of h nil, it can give me that. It gives me speak of h nil. An int is a recursive case. It only works if you can find an implicit thing for its argument, so Scala will search first for the int. If it works, then it will try and find the args, and if the whole search succeeds, then it will give me a speak of the right value. To your question. Oh, sorry, behind you, but I'm glad I answered it. To your question, this feels like it might not work because the implicit search might give us the what did I call it, speak non-int, when it actually has an int, and speak will just end up being a no-op or an identity function. It turns out the implicit resolution rules will just so happen to make that work because it finds one of them to be less specific than the other. But I'm going to tell you about how to make sure it works anyway because, well, first, I'll do that in a second. Sure, this one.
In the second implicit block,
Yes.
your output is speak of string, isn't it? That's the important, right?
Thank you. Yes, that's
And
correct.
I think it was the same case in one of the previous slides too. If you go back like a few slides back, before I think this should output be speak of string.
You're correct. Or no, I see. You're correct in what you're saying. You're talking about the output type here, right?
On the first line, the top line.
Yeah. So this is a great question. A lot of the mental gymnastics of this is sort of keeping track of when inputs and outputs are being created. I'm defining a rule. So the output of my type is the type of the rule. And the rules, the parameters on that rule are the input types. So the input type is the thing being defined there, even though it's the output of the def, which is weird. The output type is being defined inside of the speak when I say type out equals string :
Okay, so your function signature is still has the input type,
Yes.
even though it's after the colon sign, and that's technically the output.
Yes.
And why would that be so?
It's technically, well, the output is the thing called out there, right? the input over there is the output of the def. And you kind of think of it like if you were defining an AI or something like that. You're just going to define all the rules, and the AI has an engine that goes and follows the rules. When you define the rules, the output of your definition of rules process will be a thing that says input, output. So all of them are outputs of the definition process, but it just so happens that that's the input and the output per how Scala is going to interpret this with implicits and with its type system. Yes?
So one way of thinking of this is that speak object is sort of like a function, right?
Yes.
But the only thing you put on the line is what the function takes as input.
Correct.
And so it's something that takes an int tail and returns something. And to find out what it is, you have to look at the type of the line.
Yes. And I'm going to jump ahead a little bit. The fact that that's confusing is actually a big problem. It causes all of this to not work. And we'll do something later that makes all of that hopefully less confusing, in that the reason why you're confused is that there isn't enough information to look at that and interpret it properly. Scala will also find that there isn't enough information to look at that and interpret it properly. So we'll dig into that later. That was a really good question. I'm glad you asked it. And just wait. Yes?